Hello everyone, I'm Michael Tao-Yi from UC Irvine Computer Science. I will introduce STINT, Selective Transmission for Low Energy Physiological Monitoring. From March to the time of this presentation, almost 2.3 million people are diagnosed of COVID-19. Until now, nasopharyngeal swab combined with molecular diagnosis is the only effective way to diagnose this novel disease. Although it has very high accuracy, the procedure not only poses risk of exposure to the medical personnel, but also expensive to administer. To address these drawbacks, many researchers have proposed continuous on-body sensing to solve the problem of long-term uninterrupted multi-biosignal monitoring. But currently, none of the wearable sensors can withstand 24/7 continuous monitoring without draining its battery within a day or two. We need to design new sensors such that they can provide the most informative subset of sensing data while consuming minimum amount of energy. To set up the problem, we first define the baseline native system, which comprises of unconditional transmitter that transmits every raw data acquired by the sensor. To make it energy efficient, we modify the transmitter to only transmit non-zero samples. We also added a selector to generate a mask for the raw samples. The objective of the mask is to drop uninformative samples that do not benefit downstream data analytic tasks. In a nutshell, the problem can be formulated as a search problem of a selector aiming for a minimum subset of raw samples being transmitted, as well as maximization of the helpful samples being transmitted for a specific task such as disease detection. We can now look at the contour plot of energy consumption in a design space spanned by two parameters. The first parameter is the regularization strength on the horizontal axis. The other parameter is the decision threshold on the y-axis. The energy consumption clearly decreases with the increased decision threshold. To see this, we can look at the topmost portion of the plot. When the threshold is set to 1, only the samples with 100% certainty to a selector will be transmitted. Now we can evaluate how threshold affects selector performance. Precision increases when the threshold increases because the selector is becoming more conservative. On the other hand, recall decreases with increases threshold due to the increased rate of missed samples. To evaluate the overall performance, we adopted Matthews correlation coefficient because optimizing this metric MCC is equivalent to jointly maximizing both precision and recall. We also introduced a figure of merit, which is simply the ratio between MCC and the sensor energy consumption. The bottom line is that we want to increase both recall and precision, because a higher recall means lesser missed abnormal samples. In addition, higher precision suggests avoidance of sending unnecessary samples. Comparing contours of MCC and the figure of merit, we can immediately recognize their similarity. Note the boot-shaped isopleds fits completely inside the isopleds in the energy consumption contour, showing the same region of design parameters. The fact that energy consumption is roughly constant with any MCC level suggests optimizing the MCC is sufficient for maximum figure of merit. If I were to pick an optimum pair of design parameters, I would select the point indicated by the yellow star because it yields the maximal MCC and it is also closest to the point where energy consumption is minimized. With this set of parameters, potentially 14% of energy can be saved. Here are the takeaway messages. The STIM framework explores the frontier of ultra-low power wireless sensors by exploiting cheap MCU computation. The core technique of STINT is to leverage a compact deep neural network on the sensor as a proxy of the task knowledge to select and transmit only the informative parts of the raw signals. A real-world continuous blood pressure monitoring application demonstrated that STINT can potentially save 14% of the energy on healthcare IoT sensors, along with minimum recall degradation. Thank you for listening.